Uh, Good afternoon, colleagues and participants in today's session. Before I proceed, please kindly indicate with a thumbs up if you guys can hear me. Thank you. My name is Lindsay Mangwani, and I'll be a moderator for today's session. Before we begin, a few housekeeping rules. If you have any questions during the presentation, please feel free to raise your hand if you'd like to speak, or type a question in the chat, and we will notify the presenter to address it. The session is recorded. The recording will be uploaded on our CDMS and on our Moodle communities. Also, we will send a feedback survey in the chat. Would like you to fill this out for us to gain insight into whether this training was useful and how we can improve in the future, as well as providing feedback to the facilitator for their hard work. So today's session is on comparing of group techniques, and our facilitator for today's training is Dr. Anesi Kuhudzai. If you may allow me to read his bio. Dr. Anesi holds a PhD in medical sciences from the University of Antwerp, where he applied statistical models to medical research, resulting in 4 high-impact journal publications. He is a registered chartered statistician and director of ICCSSA, and is an experienced statistical and data science consultant. His career spans work in South Africa, Zimbabwe, the UK, and China, supporting over 1,500 postgraduate students and researchers across disciplines with quantitative research design, data analysis, and interpretation to strengthen research output and publication. Thank you, Doc.
say something, let's say.
Oh,
So now stop kushare, stop share.
It has screen. Kuti waone zvese
Waruna. But vaone. So kana mdadu wa zvinoita difficult my sikuchibwike
stop sharing, right?
shandira sharing about takashare screen kushare pana shanda ne avanenge vachimwetsanga means chese chamangwe
Sharp. Abu. Good afternoon, colleagues. Okay, welcome to this workshop, statistical techniques for comparing groups. Before we begin, I think there are certain things which we must make sure that, or we must ensure that we have, all of us. I shared this document, which I'm projecting. I guess you have, right? If you do not have, Doc, how can we make sure that they have? So okay, so both online and physical here. Just make sure that for those ones online, you can for those online, you can put your email addresses on chat so that we can pick them up. Then you can get this handout. Then also, you have to get the data set, which I'm also projecting here. That's the one which you are going to be using. So the document and the data set, those are the two documents which are going to use mostly the entire workshop. Then the software itself as well, you should have IBM SPSS version 32 installed on your laptop. Are we there as well? Because this is more of a practical workshop whereby I'll be doing this practically and I expect you to follow. So you must also have the software on your laptop activated. Otherwise, you won't enjoy the workshop. Whatever we do, you won't be in a position to be doing them. So so for those ones who had who have not yet installed SPSS, it seems as if we've got several people who are registering their names on chat who don't have the workshop material. Please make sure that you have the workshop material, especially the dataset and also the software itself. So you need to go to Ulink for those ones who do not have the software. Go to Ulink, log into Ulink. So for example, if you go to Ulink like this, you log in to Ulink, like what I'm doing. You put your password. You log in like this. Then you go down to UJ Tools. Are we there? You go down to UJ Tools, right? Whilst you're on UJ Tools, you go to academic or research tool software, and you go to IBM SPSS 32 here. That's where you should be, right? Once you are here, you click. Then if you do have a Windows laptop, your operating system, if it's Windows, you download this one, download for Windows. If your operating system is a Mac, you download for Mac, right? So you need some few minutes for the download to complete because the file is almost 1 gig in terms of capacity. So once you download, you quickly install, and towards the end of the installation, you are going to be required to activate the license using this code, which is here. Using this license code, which is here. Then once you're done, your SPSS should be ready to work. How many here are still installing the software who are present? Okay, I'll also give you like 5 minutes to complete this process before we continue, because if I continue without you guys having the software, then I'm talking alone. That's what it means. So please do this as soon as possible, and please download also the workshop documents, which I hope they are being shared with you. Yeah. So online participants, also make sure that you install the software. Yeah, so that we can do these things together. George, is it a question? I see your hand is up. You may go ahead if you want to ask.
I don't have a question. Sorry, it was a mistake. Sorry.
Oh, okay, it's okay. Okay, so for the time being, I'm giving you about 5 minutes to finalize the installation and download the software and install it. Okay. Okay, under normal circumstances, after you have installed the software and activate it, you need to restart your laptop. You need to quickly restart your laptop. I can see, Sydney, you are asking why the SPSS could not be existing. If you have installed the software and activate the license, quickly restart your machine for configuration changes. Then I think that should work, and your software should work. Yeah. Fortunately, this is a yearly license, so it should work until next year June. It should work until next year June. So once you have it, you are sorted until next year June. Then another issue is, if you had a previous version of the SPSS, we did have version 30 before we had version 32. You need to uninstall it from your laptop. You have to uninstall version 30, which you had before. By having 2 IBM SPSS on your laptop, it will become heavy, so it will slow down its functions. So make sure that you uninstall version 30. Then another issue is, most researchers, what I've noticed is most researchers, you do not shut down your laptop. You just sleep your laptop. And when you are using IBM SPSS, that will also cause your laptop to become very, very slow. So make sure whatever. So make sure that whatever work you do.
If you need water, there's a dispenser there. The energy cups.
So do make sure that once you are done working, you close off your projects which you have been doing, save whatever wants to be saved, and shut down. Otherwise, we shall see that if you are going to have that trend of just sleeping your laptop, over time, with SPSS included, your laptop is going to be very, 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 very slow. And I know some right now, in 5 minutes, they even can't finish installing the SPSS because their laptops are already slow because of that tendency of shutting down like books. I'll give you an example. As a human being, if you don't sleep one day, only one day, the following day you wake up like a zombie because you didn't rest. So what about our machines? You have that tendency for weeks, weeks into months, months into years. Yeah, so make sure that you stop that kind of tendency so that you shut down so that you can work well. Okay, once you download your workshop material, please create a folder. Once you download the workshop material, please create a folder. I would like you to create a folder called Statistical Techniques of Comparing Groups. Statistical Techniques of Comparing Groups. Or comparing of groups techniques, or comparing of group techniques. Then you're gonna save the material which I've shared with you in that folder, plus the output files which we are going to think throughout the workshop. We are going to have several output files, so you're gonna save them into that folder as well. So just make sure that you do that before we begin. Yeah, so I think those are the basics which we want before we start. Okay. I'm now about to start. So for those ones who are still installing, there are a few things which I'm going to be discussing which don't need the software. So I think you catch up with me along the way. Okay, so as an analyst, as a statistician or as an analyst, when you are presented with a data set like the one which you see there, you need to understand the background of the data set. That's the most important thing which you need to know. So the first thing is when you are presented with a data set, you have to understand the background of the data set, how the data was collected, the environment in which the data was collected, the variables which are in the data set, and you need to understand those variables. So in this data set which we have, the data set for this example consists of salary information and the related biographical information of employees at a certain company. So we do have salary information and the related biographical information of these employees at a certain company. So the variables or the measurements included in this example are the following. We do have gender, we do have beginning salary, which if you see in your data set, it is written as Southberg. That's how it is coded. That means beginning salary. Then we've got seniority or period of service or time. We do have the employee age. We do have the current salary, which is written as SAL now. We do have education level. We do have work experience. We do have employment category, which is written as job cut. We do have minority classification, which is minority. We do have sex and race classification, which is sex race. So these are the kind of variables which you need to relate with in the given data file. And we do have the ID or the participant number of the employees on the very first column. If you scroll down this data set, you see that at the end of the day, we do have 474 participants in this data file, which is quite a good large data set. So that's the kind of data set which we're going to deal with today. Then, since comparing of group techniques involve hypothesis testing, comparing of group techniques involve hypothesis testing, we are also going to discuss the process of testing in hypothesis in terms of the stages which are required in testing in hypothesis. That's what we are going to be doing throughout this workshop, so you need to understand it as well. Basically, when you are doing hypothesis testing, you have to have objectives in your study which gonna relate to the hypothesis which you're going to test. So you can't necessarily have hypothesis testing which is not supported by the study objectives of your study. So when you're formulating research objectives in your proposal or in your chapter 1, you need to have study objectives which are inferential in nature, so that you can formulate some hypothesis from there. If you do have descriptive kind of objectives, you can't necessarily do hypothesis testing. So that's what you need to be aware of. If you do have descriptive kind of objectives, you can't necessarily perform hypothesis testing. For example, you may have an objective to say, what is the prevalence of people suffering of maybe COVID-19 or what kind of disease at a certain area, that is descriptive. You can't necessarily form an hypothesis based on that kind of an objective. Or you'd want to assess the perceptions of students on certain topic. That is descriptive. You can't formulate an hypothesis on that. So it's very, very important that when you formulate your objectives, they relate to the kind of hypothesis which you are going to formulate as well. Because the reason why I'm explaining this is because when I view many proposals at my current position at StatCon, you see that people or researchers, they will try to develop a hypothesis where you can't necessarily develop any hypothesis. So it's very important for you to know the kind of objectives which are inferential, which then relate to the kind of hypothesis which you're gonna test, right? So hypothesis testing is an act in statistics of testing an assumption regarding a population parameter. A statistical hypothesis test is a method of statistical inference. A statistical hypothesis test is a method of statistical inference. That's the reason why I had mentioned earlier that in your objectives, you need to have objectives which are inferential in nature. At the end of the day, after testing your hypothesis, you should be able to infer to the general population where the sample has been collected. You should be able to infer your results from the general population where the sample has been collected. That's the reason why we are saying hypothesis testing is a method of statistical inference. So for you to perform hypothesis testing, the first step is you need to develop a null hypothesis. You need to develop a null hypothesis, which we normally denote as H naught, which we denote as H naught. Then you develop an alternative hypothesis, which we denote as H1 or HA. Right? Now hypothesis H0 or alternative hypothesis HA or H1, they have to be developed before you do any hypothesis testing. A null hypothesis can be also called an hypothesis of no difference. A null hypothesis can be also called as an hypothesis of no difference. Then B, you need to determine the level of significance, which is your alpha. You need to determine the level of significance, which is your alpha. So the most popular level of significance, which we normally use in the current research, is 5%, which is 0.05. So we normally use 5%, which is 0.05. Then C, you need to compute the probability value, which is your p-value. You need to compute the probability value, which is your p-value. That's where the SPSS comes into play, right? That's where our SPSS comes into play. So our p-values, we get them from SPSS. So we do have our level of significance, which we already have. Then the p-values, we get them from SPSS. Then at the end of the day, the last part is to compare your p-value from SPSS and your alpha, which is your 0.05. You need to compare the two so that you can make a decision. So the decisions are made reference to the following. If the p-value is less than, the level of significance, you reject the null hypothesis in favor of the alternative hypothesis, right? So if the p-value is less than or equal, or even equal, if the p-value is less than or equal to alpha, then you reject the null hypothesis. If the p-value is greater than alpha, then the null hypothesis is not rejected, or we fail to reject the null hypothesis, or we fail to reject the null hypothesis. So those decision criteria are very, very important in hypothesis testing, and it applies to all kinds of hypothesis testing. This decision criteria applies to all forms of hypothesis testing. That's what you need to know. So that's something which you need to know forever if you are going to be doing hypothesis testing in your life, right? Okay. Any questions before I move on? Any questions on what I've said so far? Online, any questions? Okay. I'm moving. So the first kind of comparing of groups techniques which we shall tackle is independent sample space test. Okay, before I tackle this independent sample test, what you have to know is we are going to perform, throughout this workshop, we are going to perform 3 parametric hypothesis testing techniques, comparing of groups techniques, and 3 non-parametric hypothesis testing techniques, comparing of groups techniques. There's a difference between parametric tests and non-parametric tests, right? There's a difference between parametric tests and non-parametric tests, right? So independent sample t-test is a parametric test, and we are going to do the corresponding non-parametric test of it. Okay, someone may ask, what are conditions which can inform one to do parametric tests and or to do non-parametric tests? Okay, so the conditions of doing parametric tests are that the continuous variable which you'll be using, or the continuous variables which you'll be using in performing your hypothesis testing, they have to be normally distributed. They have to be normally distributed or nearly normal. They have to be normally distributed or nearly normal, right? they have to be normally distributed or nearly normal. So the part of nearly normal is informed by what we call the central limit theorem. The nearly normal issue is informed by the central limit theorem. I won't go deep in the central limit theorem. You may research that on your own at your spare time. But those are the conditions which you need to have to perform normality, to perform parametric tests, right? So an independent sample t-test is an example of a parametric test. So in many research or in many circumstances, we aim to use parametric tests rather than non-parametric tests, because the parametric tests are more robust than non-parametric tests, right? So in most circumstances, we aim to use parametric tests than non-parametric tests because they are more robust than, in that regard. So take note of that. So an independent sample t-test is used to compare the mean score on some continuous variable for two different groups of participants. So when doing hypothesis testing, it is very, very, very important for researchers to understand, first and foremost, understand what that kind of test does. Very, very important. What that kind of test does, and whether that kind of test does it perform what you aim to achieve, which means you are now relating to your objective, right? That test, does it relate to your objective? Yes or not? If it does, fine. Then in your data set, do you have necessary variables to perform that test? For example, for you to do an independent t-test, you need a continuous variable. And I think from the previous workshops, you now understand what a continuous variable is. From the previous workshops which we've done, I've explained what a continuous variable is. A continuous variable is a variable that follows either an interval or a ratio scaled measurement, right? That's a continuous variable. So that variable should be either ratio or interval scale. That's a continuous variable, right? So you need to have a continuous variable. Then you need to have a grouping variable with two categories. You need to have a grouping variable with two categories. So for example, we wish to compare the current salary of males and females. Thus, do males earn better than females, or it is the other way around in this company, which we have? That's what we want to test, right? So which then means that the categorical variable which we have is gender. That's the categorical variable which we have, or that is the grouping variable which we have. So whenever you have to do an independent t-test, you need to have a grouping variable or a categorical variable with two levels. So in this case, it's gender. And the two levels which we have are males and females. Then the continuous variable which we have is current salary. So we go now to our data set. So what we are dealing with here is we are saying gender, right, is our categorical variable. If we go to our variable view here, you see we do have 0 as males and 1 as females. So this is the categorical variable or the grouping variable which we have with two levels, males and females. Understand? Then the next thing which we want is the continuous variable. And according to our notes, we are saying the continuous variable is current salary. So we say this variable needs to be continuous. It needs to be of scale, variable, or interval, or ratio. So which is sound now. So sound now here, as you can see, that is our continuous variable. So now our aim is to check whether this salary for males and females, does it differ significantly, right? That's what we want to check. So now in my notes, I've been generous enough to write the procedure which on your own you can follow to perform the independent test on your own, right? So in case you also lose when I'm going through, you can also refer to these steps. These are the steps which you follow when you want to do an independent test, right? So now let's do the test now, right? Let's go to the data set and do the test. I hope now, with these minutes which I was explaining in the previous version, previous things, you now have your SPSS working on your laptop. And now let's do the analysis, right? So let's go analyze. Okay, so for the time being, you can follow what I'm doing instead of reading the steps, unless if you are lost. So analyze, compare means and proportions, right? Compare means and proportions. Then we move on to independent sample test. Are we here? Right? Then we click independent sample test. Our testing variable is our continuous variable. So that's our salary now. Then we put him here, right? Our grouping variable is the gender, right? We take our gender, then we put him here. Then we do have these question marks. How do we erase these question marks? We erase these question marks by defining the groups. Defining the groups means we have to know the codes which we have for these different groups. So how do we know the codes? The codes, we know them by going to the variable view. You go to gender, so I can put this one aside so that you can see. You go to gender, you go under values, under gender, you click here. So these are the codes, 0 for males and 1 for females. So these are the codes. Once you take note of these codes, you click OK. You go back to where you're analyzing. You click define groups. You replace where there's a 1, you put a 0. Where there's a 2, you put a 1, right? Then you click continue. Then you click options. You see here the confidence interval is going to be calculated using the 95% confidence interval, which is correct. Then you continue. Then you click homogeneity of variance test. You click homogeneity of variance test, and you make sure that estimate effect sizes is also clicked. Then once you are like this, you can see our OK is active, and you click OK. Then you get this output file. From here, this is your output file. Then you go down until here. So we will go through this output file and try to make sense out of it, right? For those people, for those researchers who are like me, who have been using SPSS before, this SPSS is SPSS version 32, which we are now using. You can see that if we compare the outputs which we see in version 32, they are quite different with what we used to see in version 30, in version 31 and others. But anyway, UGA last used version 30. And other universities, they are still using version 31. You can see that version 31, version 30 going behind. The way they produce the output of independent test is a bit different with what we see now with version 32. So I had to rework my slides so that I can suit the current version which we have. Okay, so going back to our notes, the first step which you need to do when carrying out an independent t-test is step 1, which is the Levin test for equality of variances. So you need to carry out that step before you do the actual independent t-test. So step 1 involves testing if the variances of males and females are equal. So in order to do that, we also need to identify the null hypothesis and the alternative hypothesis respectively, just as we have agreed in our steps earlier here that the first step in hypothesis testing is to identify the null and the alternative hypothesis. So that's exactly what I'm doing here. So I have to identify this null hypothesis and the alternative hypothesis for testing the equality of variances, which is going to be H0, the variances are equal, and H1, the variances are not equal. Then from there, I do my analysis, which we have just performed together, and I have to identify the homogeneity of variance test. So going back to the output file, where is my homogeneity of variance test? If you go down here, this is where you find your homogeneity of variance test here, right? So this is the table which you then see in my notes here. This is the table which you see in my notes. This is where I got it from, right? Now, my alpha or my level of significance is 5%, right? 0.05. Then, so I now have my alpha, which is my level of significance, which is 0.05. Now, I need to look for my p-value. So in these notes, right, or in this output from SPSS, my p-value is determined by sig. So in SPSS, wherever you see a sig, in SPSS, wherever you see a sig, that's your p-value, right? So this is our p-value. So here, the p-value is said to be below 0.001. The p-value is said to be below 0.001, right? Are we together? So we will use a 5% level of significance when looking at the Levin test for equality of variance table above. The p-value, which is the sig, is less than 0.001, which is less than 0.05, right? So we reject the null hypothesis. Right? Meaning that the variances for males and females are unequal. Are we together? So the p-value less than 0.001 is less than 0.05, right? So we reject the null hypothesis, meaning that the variances for males and females are unequal. Are we together? Any questions? Comments? Okay. Now that we have established that, okay, yes. Okay. The first step we said, okay, so I think maybe I'll switch from this page to the other page. So we said the first step of hypothesis testing is to identify your null hypothesis and your alternative hypothesis. That's your A. Going to what we have done here, you see that this is what we have done here. We identified our null hypothesis, which is the variances are equal. We identified the alternative hypothesis, which the variances are not equal. Right? Then let's go back to step B. Step B is to determine the level of significance. So I think I've mentioned that the level of significance which we normally use in research is 5%, which is 0.05. Right? Then step 3, is to compute the probability value. And I think I've told you that the computation of the probability value is done by SPSS, right? Which is exactly what we've done. And we got this output file. And I took this table to our notes and I placed it here so that it can be easy for us. Then part D, step D, is to compare the alpha, which is your 0.05, with this p-value which you have. Then the last part is to use the decision criteria, which is indicated here, that if the p-value is less than alpha, you reject the null hypothesis. And that's exactly what we've done, because our p-value is less than 0.001. A value less than 0.001, statistically, it is less than 0.05. So, which means we have to reject the null hypothesis. So we reject this null hypothesis and we go with the alternative hypothesis, and we agree that the variances are not equal. Understand? Any other question? Okay, let's continue then. Then let's move on to step 2. The step 2 is whereby we are now testing the equality of the means. That is where we want to now check whether the average salary of the males versus the average salary of the females, are they more or less the same or they are quite different, right? So the next step is to finally test whether there's a difference between the current salary for males and for females. If you go to the independent sample t-test table, okay, I want to show you where I got this table, If you go back to our analysis, if you go up, this is the table which I've copied. This is the table which I've copied into our notes here, right? So this is the table which is going to be used to test for equality of means. So you can see that in this table, there are 2 rows. The first row here is equal variance assumed, right? And the second row here is equal variance not assumed. So which means we've got 2 solutions, or we've got 2 results for the equality of means, right? Based on the variances, whether they are equal or they are not equal. So we have to choose which of the row to use here, either these results on top or these results on the bottom, based on our step 1. You don't just do guesswork, right? You don't just do guesswork when you are here. So because from step 1, we have established that the variances are what? Unequal. It then means that when you go down to your step 2, you have to go with the row where equal variances are what? Are not assumed. So which means we're gonna go with the bottom row. That's where our results are going to be looking like, right? Then when we are using the bottom row, we now need to check whether are we using a one-sided hypothesis or a two-sided hypothesis, right? So in our case, we are using a two-sided hypothesis because we are saying there's no difference between the groups. Someone may ask, what is the difference between a one-sided hypothesis and a two-sided hypothesis, right? With a two-sided hypothesis, we are saying there's no difference, which means whatever result, whether the difference between the groups, let's say right now we are comparing the salary between males and females, right? We are saying there's no difference between the salary of males and females. That's two-sided. Because it's either we accept whether the salary of males is higher than the females or is lower than the females. That's two-sided, right? But the moment when you formulate your hypothesis to say male salaries are higher than female salaries, already that's a one-sided kind of hypothesis. Are you seeing the difference? The moment when you take a side, whether something is positive or negative, then your hypothesis is one-sided. But the moment when you say there's no difference, it's two-sided, you are willing to check both sides, right? So our hypothesis is two-sided, hence we have to take our, so which means we are taking this p-value here below, informed by the issue that our variances are unequal, and we are taking the two-sided, informed by our hypothesis that there's no difference. So we are taking this p-value. I know some researchers, for example, here, you might say all of these four p-values, they look the same. Yes, they look the same. But it's very important to know which one to go with. And why are we doing that? And why are we picking that one? To you or to someone might think that there's no difference and it's not important, but it's very, very important to know which exactly out of the four to pick. Why? And what are the reasons behind picking that particular p-value? So we are picking this one, right? So we will use a 5% level of significance. When looking at the t-test for equality of means table, the p-value is less than 0.001, as you can see, less than 0.05. So we reject the null hypothesis. We reject this null hypothesis that there's no difference between the groups, and we go with the alternative hypothesis, which is saying there's a difference between the groups, right? So this suggests that there's difference between males and females when looking at the current salary. That's what we come up with. So that is statistically significant, that there is a difference between male salaries and female salaries. That's what we are getting from our analysis, right? Now that we got the difference, that there's difference between males and females, it is now very interesting now to see the difference. Where is the difference emanating? And what are the numbers behind the difference? So we can now go to the group statistics table below to see what the means for each group is, right? So if we go back to our analysis, we go to this group statistics table. That is the one which you see in my notes here. That's where I got it, right? So in the group statistics table, it is evident that males are earning 16,576 on average, 0.71, right? And females are earning 10,412.77 on average. So those are the average salaries which the males and the females are earning, right? And according to our statistics, this difference is statistically different, right? So we've managed to prove that the current salary at this particular company between males and females are statistically different. And we can also relate how they are different by the average mean values which we have, right? Okay. Any questions up to now? Any questions up to now? Okay, yes, let's have the question. Or maybe it's a comment. Let's have it.
Some afternoon, Prof, and all stakeholders present. I'm requesting that Prof just shares how you got to the analysis on SPSS. I was just still installing by the time you explained that analysis step there on SPSS, so that you get to these results that we are now interpreting.
Oh, okay. Okay, before I do that, another question, if it is there. Is there another question?
No, Doc.
Okay. Okay, so for the time being, I'll close this output file for the time being. Then this is my data. So I did say we go analyze. Then you go compare means and proportions. You click independent samples t-test, right? Okay, let me just do say reset. You take your sound now, that is your continuous variable, you put him there. You take your gender, that's your grouping variable, you put him there. You define groups based on your variable view. From the variable view, we saw that group 1 is a 0, group 2 is a 1. Then we continue. Then we went options and we verified that our confidence interval percentage is 95, and that's what we want. So we continue. And we also include the homogeneity of variance test here. Then we then say, okay, that's how I got to this output file. Okay, now that we are here, let's save our output file, all of us. Let's save the output file, all of us. So we go file, you go file, you go save as. So I think I've asked you earlier that you create a what? A folder. So in your folder, I expect the data file to be in your folder. I expect the document to be in your folder. I expect this output file again to be saved in that particular folder, right? So myself, okay, let me just look for my folder. I think my folder is under StatCon. Then I think I've got workshop material, and this is comparing of groups techniques. So I'm going to save my output there. So when you're saving your output, you start by the name of the analysis which you've done. So you're gonna say independent samples t-test, then followed by the name of the variables which you've used, right? So my variables are current salary versus gender. Then you say save. So you need to be organized when you're doing these things. You need to be organized. So when you share this file or this output file with someone, before that someone opens, he or she can see that this is an output file which I'm expecting to see an independent samples t-test where current salary was being compared between what? Males and females. Self-explanatory, right? So that's what we expect. You need to be organized like that. Then you say save, right? Yeah, so this is how you do it. Okay. If there are no questions, further questions, I'm continuing. Okay, step 3. Step 3 involves checking the equality of means or testing the difference between the current salary of males and females using confidence intervals. So what we did earlier, we were using the p-value, is it? But you can also use what? Confidence intervals, right? You can also use confidence intervals. The mean difference between the two groups can also be checked using the confidence interval. In order to test it, there's a difference between the post-test marks. I think this was supposed to be current salary for males and females. We need to identify the null hypothesis and the alternative hypothesis. So there's no difference between groups. There's a difference between groups. And we go back to this table. We go back to this table. And we use that bottom row. Well, that's what we decided that we are going to be using, isn't it? And these are the confidence intervals. The lower confidence interval is 5,126. The upper confidence interval is 7,201, right? So how do you determine whether this confidence interval is statistically significant or not? That's the question, right? For you to determine whether the confidence interval is statistically significant, you do it by seeing whether between the lower confidence interval and the upper confidence interval, between those two, does 0 pass in between the two? Are you getting the sense? Between the two, is there 0 there in between? If there's no 0, then it means the confidence interval is statistically significant. Are you understanding this? Eh? This confidence interval, does 0 pass through this one? Eh? No. Yes. So which means it is statistically significant. If 0 passed through this confidence interval, it means that confidence interval is not statistically significant. Are we together? Yes. Mm. On the number line. The normal number line. Yes. 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 If, let's say, your lower confidence interval is negative and your upper confidence interval is positive, it means 0 is passing through. So that a confidence interval is not statistically significant. That's what it means. But these ones, they are both positive. So there's no way you're going back. So, or if they are both negative, then it's statistically significant. Mess. Yes. Mm. So I'm saying if the lower confidence interval is negative and the upper confidence interval is positive, 0 is passing through that interval. So that means that confidence interval is not statistically significant. If they are both negative or both positive, it means that interval is statistically significant. Understand? Okay, fine. Okay, we are done with confidence interval. Let's say you are writing a paper or you are a PhD student. Going an extra mile by calculating what we call the effect size gives you some, your document looks a little bit, you see. Yeah, so calculating the effect size for the independent test will give you that impetus of the document to say, hey, this person, yeah, at least. So since there's a difference between males and females when looking at their current salary, it is important to calculate the magnitude of the difference. Now we know the difference, 16,000 versus 10,000. What is the magnitude of that difference? So eta squared statistic can be used to calculate the magnitude of the difference. Eta squared ranges from 0 to 1 and represents the proportion of variance in the dependent variable that is explained by the independent grouping variable, right? So in this case, we do have a formula of calculating the eta squared, which is t squared over t squared plus n1 plus n2 minus 2. That's the formula which we use to calculate the eta squared. So we get these values from our table. So we are getting these values from this table. And we agreed that we are using the bottom row, right? So your t squared from the bottom row is here. This is where now, if you thought you were clever here, whereby you were doing your guesswork of taking any p value and you thought you were clever, here you won't be clever now. because these two values, they are totally different. So if you didn't get the principles of which row to use, then here you are going to be stuck. Because basically, you can see here that these t values, they are different, and you have to know which one to pick. So according to what we agreed, we are using the bottom row. So our t value, which you are going to use, is 11.688, right? Then squared, then we repeat it here. Then N1 means sample size for group 1. That's N1. So where do we get our N1? You go to your results, and your group 1 is males, and your N is 258, right? That's where you get your N1. Then you go back. On our formula, you need N2, right? Where do we get N2? N2 is the sample size for what? For group number 2, which is females, which is 216. That's when you get your what? Your N2, right? Then you go back, you put your N2 in your formula, right? Then minus 2 degrees of freedom. This is already in the formula, then you put your minus 2. Then when you simplify this, you must get 0.22 to 2 decimal places, right? So all of us, we've done maths or statistics at some point. You're going to prove my calculations whether they are correct. If they are not, please kindly write me an email or phone me to say your notes, they are misleading, the calculations are not correct, then I will correct. I did this under pressure last night. I think you saw my email, it was like AM. So when I was preparing this, so yeah, I could have made some mistakes. Then once you have this value to 2 decimal places, you then compare it with the Cohen 1988 guidelines, which are 0.01, it means small, 0.06 moderate, 0.14, it means large effect, right? So this value, 0.22, is greater than the large effect, which is 0.14, which means the difference between males and females in terms of their current salary is very large, is of large effect. So if you are writing a paper or a PhD, that will be wow, you see, by having this added in your paper, right? Good. Yes, I'm also done with the independent sample t-test. As you can see, this is the robustness of a parametric test, all those steps. So yes, we are done with the independent sample t-test. Any questions?
They're asking, do we perform this manually?
Yes, as you can see, it's done manually most. Okay. Whilst we are there on calculation of the effect size, yes, you can see that it's been done manually. However, the current SPSS do have a table for effect size here, the last table here. So we do have these point estimates which you can compare with, but this is coming from Cohen's D. This is what we call Hedges correction. This is Glasses delta. So you need to have literature which you can use to compare with this Cohen's D or this Hedges correction or this Glass delta. If you do have this literature which you can use to compare with either of this, then there's no need of using eta squared. So far, I haven't got the literature to compare with these three. That's the reason myself I'm using the eta squared, which I know I can compare with the Cohen's D. So as long as you have got literature which can relate to these three, then you can be saved from manually calculating the eta squared. Because these are also effect size statistics here, which you can use, but you need to relate them with some literature to prove that 1.009, is it a large effect? Is it a very large effect? Is it small? Is it moderate? Where are you getting it from? So you need to compare this with literature. then you can avoid calculating. Myself, I know Cohen, 1988, who compares with the eta squared. That's why I had to do this manually. Answered? Question?
Yes, please. Could you please take it back to the SPSS article?
Here we go.
Okay. Okay. No, please take it up a bit to the. Yes. Yeah. I don't know whether you explained that when I step out the standard error difference. It doesn't have any relevance to our analysis.
No, it's not relevant.
So we just skip it.
Yeah. So in any SPSS output, you need to know what to report and what not to report. I think that's the relevance again of these workshops, that we assist you to explain what is it which is relevant to report and how do you report it and what is not relevant to report. Very important. It's not when you get this output, especially from us statisticians, you need to know what to report and what not to report. You don't report everything. And also how to present it either in a thesis or in a paper. You also need to know how to do it. Because, for example, if you are writing a paper, right? How many tables do we have here? 1, 2, 3, 4 tables. You can't present all of them like the way they are in a paper. Because most papers, under other guidelines, they will tell you that they need like a maximum of 6 tables, the whole paper. So if you are not skillful enough to compile all those tables into something, maybe one table, which can encompass all those results in one, then you are in trouble because your paper won't be published because you'll be having so many tables. So in a thesis or in a dissertation, yes, you can copy and paste because you can go as much pages as you can, maybe, especially in a thesis. But in a paper, you can't because there's limitations of number of tables required in publishing. So you need to know how to report these results. Yeah. Okay, any question? Okay, nothing here again. Good. So let's move on. Before we move on, we've saved our output, and this is the name of the output, right? Independent SMOT test, current salary versus gender. That's the name of our output we've saved, right? Now, let's close this output. Let's close this output because we've saved it. Let's close it. The moment when you don't save it, you see that whatever we're going to do next, it will fall under. And to me, that's not a good practice of analyzing data. Then let's move on to the Mann-Whitney U test. Okay. Okay. The Mann-Whitney U test is a non-parametric test used to test for differences between two independent groups on a continuous measure. So the Mann-Whitney U test, it does the same thing as what we did earlier, but it's a non-parametric measure, meaning maybe you've tested the current salary and you've determined that it is not normal, then you go with the Mann-Whitney U test. So let's apply the Mann-Whitney U test in exactly what we did earlier. So all of us, let's go to our data. All of us, let's go to the data file. Let's go analyze. Let's go analyze. Then let's move on to non-parametric tests. Are we there? right? Then we move on to Ligas dialogues, non-parametric test, then we move on to Ligas dialogues. Are we there? Then we go to 2 independent samples. So that's the journey which we have to move. Are we there? Okay, then we click 2 independent samples. Then we take our salary now. We put him under test variable. We take our gender. We put him under grouping variable. We define our groups. Remember 0 and 1, right? Continue. Options, descriptive, right? Options, descriptive, right? Continue. Then we make sure that Man Whitney is ticked. Then we click OK. Right? Are we there? Okay, good. So I'm going to discuss the ranks, but they're not important even to report in any dissertation or thesis or paper. It's not important to discuss about the ranks. Being a non-parametric test, the Man-Whitney test calculates a mean rank for each group. The ranks are compared to each other and not the means as with the parametric test. So remember, with the parametric test, we use the means, but here they use the mean ranks to compare the groups. So if we find a difference between males and females, it will indicate that these groups are different based on the ranks. That's what it means. In order to test if there's a difference between the current salary for males and females, we need to identify the null hypothesis and the alternative hypothesis. So that would be the same kind of hypothesis which we used earlier. H0, there's no difference between the groups in terms of their current salary. H1, there's a difference between the groups in terms of their current salary. Then when looking at the test statistics table below, this table, I took it from this analysis. I took this, then I pasted it here. The p-value, which is the asymptote sig, so here the p-value is the asymptote sig two-tailed, is less than 0.001, is less than 0.05. So we reject the null hypothesis. Thus, there's a difference between males and females when looking at their current salary, right? So here there's no need of checking whether there's the variances are the same or not. There's no need. We just go straight and do our hypothesis testing, and we see that there's a difference, and done. So that's the difference between a parametric test and a non-parametric test. With parametric test, we've gone through all those steps, but here we just go to the point, we reject or we don't reject. Is it clear? Then from there, we can do that extra thing of calculating the effect size. So in this case, the effect size is calculated by that formula. R is equal to Z over square root of N, where N is the total number of cases. Then for this calculation, the negative sign in front of the Z value should be ignored. So if you go to your results, you see that your Z is minus 12.286. So you ignore the negative sign when borrowing the Z from this into the formula, you ignore the negative sign. Then you insert your R is equal to 12.286, square root of N. Your N is the number of cases or the number of participants, which is 474. Yeah. Then if you simplify the two, you must get 0.56431 like that. To 2 decimal places, you get 0.56, and you compare with the COE 1988 guidelines. You can see that the COE 1988 guidelines for independent tests, they are different with the Mann-Whitney U test. So which signify the parametric and the non-parametric. So 0.1 is small effect, 0.3 is medium effect, 0.5 is large effect. So in this case, it's 0.56, which implies that this is a large effect. Understand? Done. So Mann-Whitney is done. Very simple. Any questions? Comments on Mann-Whitney?
In line with
Yeah.
someone is asking to please repeat the data cells by the settings.
Ish. I'm sorry, but let's be attentive. I will repeat, but let's be attentive when I'm doing this. Okay. For all information, I think this is my last hybrid session. The next coming sessions, they'll be physical. I'm serious. This is the last hybrid session. Okay, I'll close, then I'll repeat. So analyze non-parametric tests, Ligas dialogues, then 2 independent samples. Right? Okay, I'll click reset so that I'll start afresh. So now under test variable list, gender under the grouping variable, define groups, 0 and a 1 there. Then continue, options, click descriptive, continue. Then you make sure that Mann-Whitney is ticked, then you go okay. Then let's save our output file. Let's save our output file. So you go file, save as, so you are saving in that folder. So instead of typing everything, I can click independent sample t-test there, right? Because I had it already. Then what I'm going to do is I'll just delete here. Then I'll just say Mann-Whitney U test. I'm done. So this is my file name. So let's save our output. Let's save our output just like that. Let's save our output just like that. Are we there? Are we there? Then we save. Right? Any other questions? Is there something again online? No. Okay, then we close. Okay, so let's move on. We are moving on to one-way analysis of variance. We are moving on to one-way analysis of variance. Okay. Okay, so with one-way analysis of variance, it is used to compare the mean score again on some continuous variable, but now it is for 3 or more groups or levels, right? That's the difference between a t-test and a one-way ANOVA. So a one-way ANOVA, we are now dealing with 3 or more levels, right? So in this case, we wish to compare the current salary for 7 employment categories, right? For 7 employment categories. So let's go to our data file and check what is these 7 employment categories. I think this is the job cut, right? So we go variable view, then we go job cut, then we click values so that we have an idea of what we are comparing with, right? So in this case, we are supposed to compare current salary of a clerk, office trainee, security officer, college trainee, exempt employee, MBA trainee, technical. So we are going to compare whether their salaries are statistically significantly different, right? That's what we want to check. So we do a what? A one-way ANOVA. I chose an example which can relate to any discipline, right? That's the reason why I chose this example. It relates to any discipline, and everybody can relate to salaries and job positions, right? But you can apply this same concept of independent test one-way ANOVA to any discipline, right? As long as you've got a continuous variable, two groups, continuous variable, three or more groups, you can do one-way ANOVA in any discipline. But this general, so that no one feel that maybe I'm concentrating with social sciences or I'm concentrating with medicine, example, this general. I think all of us, we can relate to this. Okay. So now, these are the steps which you can follow when you're alone. But now, let's do as I'll be clicking. Then when you're on you can practice using these steps. So let me do the analysis. Online, please be attentive. Let's not have that question again of repeating. Right? So analyze, compare means and proportions, then one-way ANOVA. Are we here? Are we here? Okay, then under dependent list, we're gonna put our SAO now. Then our factor is our categorical variable, which is going to be our job cut, right? We put him here. Are we there? Then we click post hoc. We click post hoc. Then under post hoc, we've got equal variance assumed. Under equal variance assumed, we click Tukey. Under equal variance assumed, we click Tukey. Then we also have equal variance is not assumed. Under equal variance is not assumed, you click Danest T3. Right? Then you click continue. Right? Then you go options. Under options, under statistics, you click descriptive, you click homogeneity of variance test, you click Brown foresight, you click means plot, and you make sure that the confidence levels or intervals is 0.95. Make sure all those things are ticked. Are we there? Then we click continue, and you make sure that the estimate effect size for overall tests is ticked as well, right? Then you click OK. Then you get your what? Your output file. Immediately, let's save our output file, right? Immediately, let's save our output file. So we're gonna save file, save as. Then myself, I'm used to this, so I do this. Just do this. Then I say one way ANOVA test between current salary and what? Job cut. Then I do this, say against job cut. Something like this, right? That's my right? Then click save. Then it will appear here, right? It will appear here. Are we there? Okay. Let's go to our notes. Step 1, Levin test for homogeneity of variance. So the interpretation of this is also a bit long, like the one for independent t-test, because it's parametric and it's robust, right? So Levin test for homogeneity of variances, in order to do that, we have to identify the null hypothesis and the alternative hypothesis respectively. H0, the variances are homogeneous. H1, the variances are not homogeneous. And we will use a 5% level of significance, right? So we need to have the test of homogeneity of variance there. If we go to our results, I picked it from this table. Then from here, I took it to here, right? I took it to there. So the p-value sig based on the mean. So we do have these p-values based on different things here. So ourselves, we use the one based on the mean. It is less than 0.001, which is less than 0.5. We reject the null hypothesis, suggesting that the variances for the 7 groups are not homogeneous. Suggesting that the variances for the 7 groups are not homogeneous. Right? Are we there? Are we there? Okay, so once we've established that the variances are not homogeneous, we move on to step 2, right? So under step 2, we now want to compare the current salaries of the 7 employment categories. However, the reason why we did the issue of the homogeneity of variances is to make sure that if the homogeneity of variances are assumed, we use the ANOVA table. If the homogeneity of variances are not assumed, we use the robust test of equality of means table. So that is very, very important. So you see that if you go to your analysis here, we do have the ANOVA table here, and we do have the robust test of equality of means. Right? Both tables, the ANOVA and the robust test of equality of means, they are used to determine whether there's a statistically significant difference in current salary among the what? The 7 employment categories, depending on the homogeneity of variances. So it's very, very important again to know which table to use, either this one or this one. So since from step 1 here, we have determined that the variances for the 7 groups are not homogeneous. It means we are not going to use the one-way ANOVA table. We are now going to use the what? The robust test of equality of means to determine whether there is a statistically significant difference, right, in current salary across all those what? 7 employment categories. So, and this is the p-value. So you come here and we finalize that surely there's a difference between the current salary for employees in the 7 employment categories. Are we there? Are we there? Any questions, comments? Okay, yes. Yeah. Are you referring to step 1? Yeah, we rejected this one, right? So we agreed that the variances are not homogeneous. And when going to step 1, if the variances are not homogeneous, you use the robust test of equality of means table, which is this one. You get it? Thank you. Any other question? No. Okay. So now we've established that there's a difference in the current salary of these 7 employment categories, right? So in statistics, according to one way and over, once you establish that there's a difference, you don't end there. Would want to know, right? Would want to know where the difference lies, right? So if we go to our variable view, we go again to our employment categories, we're interested to know that the difference lies between clerks and office trainees, clerks and security officers, clerks and college trainee, clerks and exempt employee, clerks and MBA trainee, clerks and technical. So for each and every category, we have to compare it against each and every category so that we determine where the difference lies. And that's a lot of work, right? That's a lot of work. So one way ANOVA is brilliant because it then creates what we call post hoc tests or multiple comparisons tests, which you can see here. So you see here, clerical, we compare with office trained clerical, this clerical, this clerical, this clerical, this clerical, this. We are comparing clerical against the other 6 employment categories. Then we also go to office trainee, we compare it against other employment categories, right? To check where the difference lies. However, there is something which we need to take note of from the notes again, based on the issue of the homogeneity of variances, right? Based on the issue of the homogeneity of variances. Because there are more than 2 groups, we don't know between which groups the differences are, right? Thus, we have to look at the multiple comparisons table or post hoc test to determine this. So if the homogeneity of variances were assumed, you use the Tukey test. If the homogeneity of variances are not used, are not assumed, you use the density test, and you will use a 5% level of significance. Each pair of groups is then tested in the multiple comparison table, right? So in our case, which test do we use? In our case, which test do we use to compare against each other? Which test do we use? Dynasty 3, right? We are together, dynasty 3. So we go down. So everything here is about Tukey and until here. So dynasty 3 starts from here, right? So here, the first comparison is clerical against other job categories, right? The nice part about SPSS is where there's a statistical significant difference among the post hoc tests it will give you an asterisk. This one. That's the nice part about SPSS. Where there's a statistical significant difference between the two categories, there's a what? There's an asterisk. If you go across in the same row, you can even see that the p-value is below 0.05, which means it will be also statistically significant. Understand? That's the nice part about SPSS. So where there are all these asterisks, it means there's a statistically significant difference. So which means the current salary of the clerks is significantly different with that one of a security officer, that one of the college trainee, that one of the exempt employee, that one of the MBA trainee, and that of the technical people. Only with office trainee, that's where there's no much difference. Right? That's what it means. Then you can go to another category and you can compare again. Right? That is about post-hoc tests. That's how they work. But remember that there will be also some repetitions. For example, clerical and office trainee here is the same as office trainee and clerical. So when you are writing down your results, you must avoid such repetitions. Right? Then, so that is all about multiple comparison tests. But now you can then see that we can go further now to the descriptive table to check how the difference is, right? So for example, you can see I think you saw that in our Dynasty 3, the clerical salary were not much different with the office trainee, right? But with others, they were statistically significant different, isn't it? So you can see their mean values here. The clerks, they are getting an average of 11,134.82. The office trainees are getting 11,136.41. It's almost a difference of very, very little, right? That's the reason why you couldn't see even a statistical significant difference between the two job categories in terms of their current salary. But as comparing with others here going down, you can see that they are different. And our states determined that the difference was what? Was statistically significant. So now you can explain the difference in the average salaries using the descriptive table. Understand? Okay. Once you have done that, the last part will be the calculating of the effect size. Right? The last part will be the calculation of the effect size. So this is the formula to calculate the effect size, which is the eta squared, sum of squares between groups over the total sum of squares. And you get these values from the ANOVA table. You get these values from the ANOVA table. So if you go to ANOVA table, sum of squares between groups and total sum of squares. So sum of between groups is this one over total sum of squares, which is this one. You divide the two, right, to calculate your eta squared. Then I did kind of round off my values. Then I simplified to 0.69. But with this current version of SPSS, we are blessed now, because if you can go down to the effect sizes, you can see that now eta squared is also included among the effect sizes in the current SPSS. So you may ignore that calculation and just get your answer from here, right? So we are a bit blessed here. So your point estimate here is 0.687 eta squared. And 0.687 there, you can even see here my calculations 0.68773, and so I was quite correct, right? Yeah. So my sums are still going fine. So this and this are exactly the same. Then we compare with the COE 1988 guidelines. 0.01 small, 0.06 moderate, 0.14 large, and 0.69 is very, very large because it's over 0.14. I don't know how many times. So yeah, the difference in salaries is quite huge. That's what it means across all those 7 employment categories. That's what it means. Done. That's about one way and off. Quite a long analysis. And it needs skills to know how to report this. It needs skills to know how to report this and put up the tables. And I think you saw there are so many tables. How do you present this in a paper? How do you present this in a thesis, in a dissertation? To save the amount of tables, it needs skills. I've wrote some papers among my publications. Among my publications, you can see some papers which I have written. You may refer to those papers and see how I presented this kind of analysis. Always I do is sometimes is what I preach. Okay, the BMC Women's Health. I think this was a paper on gender. I did some one way and over in that paper. Okay. Okay. Okay, so you may look for this paper. That's where you can see where I published about ANOVAs. Yeah. So you can see how you can present this in a paper. Yeah. So that's how I presented. So you find that I had to squash all those tables into this. That's why I'm telling you that you need some skill to do it. So yeah, I can refer you to this publication. Okay, thank you. Any questions before I move on to the other to Crookes or Wallis, which is the non-parametric version of one way and over? Yes. It is based on this table. So you do have your hypothesis, right? Then you do have this table from your ANOVA results.
As the variances are assumed or not assumed.
This is your hypothesis. H naught, the variances are homogeneous. then H1, the variances are not homogeneous. So if the variances are homogeneous, they are assumed. If the variances are not homogeneous, they are not assumed. Yeah. Yes. The mean. The mean or in the output, it is just showing you this graph. The mean plots. It's just plotting the average current salary of those job categories. So I think we agreed that the mean salary of clerical and office trainee was around 11,000. That's why you see it's like this. Then the security, what did we say about? If you go back here, you can relate this table with your graph. This table, you can relate it very well with the graph. For example, security officer is 12,375. You go back here, you can see a 12 point something here, right? Yeah. So it's a plot of these figures. Yeah.
There's no need to report it, right?
When you're writing,
Yes.
maybe in a thesis or in a dissertation you can include, but in a paper, a paper is always limited by the other guidelines. So sometimes you don't have time to shine like it and put that plot. Maybe in a dissertation or a thesis you can. Any other question online? Do we have anything?
Yes. Right. Would you recommend SPSS for efficiency?
For
efficiency?
Okay, the reason why we use the SPSS is because it's a more of a point and click program, which is cheap to almost everyone who wants to learn statistics and analyze data. ARA, you need some programming skills. Yes, we can do this in ARA, very, very fine, but you need your programming skills to be of top notch. And I personally, I don't normally use ARA in these workshops because there are not so many people with the skill of programming. But with SPSS, point and click is cheaper. Yeah, because most of the things are already programmed. Yeah. I'm opening this so that someone can just see the syntax and see how it is. Yes, I do this in ARA, but yeah. You see, that's the, well, we do have another ARA studio, okay, remind later. So these are the kind of things we should be doing when you're doing ARA, this kind of programming. So it's not everybody's tea of coffee. So that's the reason why we do SPSS. Answered? Okay, another one? No questions? Okay, let's continue. Okay, so now we are doing the Crookes-Wallis, which is the non-parametric version of one-way ANOVA. We are still going to be using the same variables, the current salary and the job category. So let's go straight into it. Let's go to our data. I hope everyone we've saved our file, and to avoid our output, which we are going to do going under, we close here. Right? Yeah. So now, okay, all of us, let's be attentive, analyze, right? Non-parametric tests, Ligas dialogues, then K independent samples. Then we click K independent samples. Are we there? We take our salary now. We put him there. Job cut. Then this one, it needs to define the ranges. That's why it's now giving us our question marks in this red. We have to define the ranges. So what we do is we put this one aside. We go to our variable view. We put it down like this. We go to job cut. We go across to values and we click here. Right? How many categories do we have? 7. So from category 1 to category 7. So that's the information which we need to take to our question mark. So we click OK. We put back this one. We click define range. Minimum is a 1 and maximum is a what? It's a 7. The reason why this one asks like this is because you can limit the range. Maybe you may want to only compare the first 3 job categories. So which means your maximum will be 3. If you want to compare only the first 5, you can do. Or you can say 2 to 4, 2 to 5. Yeah, you can play around with your ranges. Then you click continue. Of which, that's also the better part of Crooks or Wallis. Yeah. One way or another doesn't give you that option. The one which we just did. Then you click options, you click descriptive under options, you click continue, you make sure that under test type, Crooks or Wallis H is clicked, then you click OK. Are we there? Then you click OK. Right? Then let's go to our notes. So as usual, being a non-parametric test, the Crooks or Wallis test calculates a mean rank for each group. So the ranks are compared to each other and not the means with the parametric test. So if we find the difference between the employment categories, it would indicate that these groups are different based on the ranks. So in order to test if there's a difference between the current salaries for employees in 7 employment categories, we need to identify the null hypothesis and the alternative hypothesis. H0, there's no difference. H1, there's a difference. And we use the 5% level of significance. Then we just take this result into our notes. And we have this p-value is less than 0.05. So we reject the null hypothesis. And we conclude that there is a statistically significant difference between the current salaries for employees in 7 employment categories. Done. Are we there? This one, there's no homogeneity of variance, assumed, whatever. It doesn't even have the post hoc test to check where the difference lies. Very simple like this. Simple and efficient. The efficiency.
Not robust.
Yeah, it's not robust. It is. Yeah, it's not. It's not robust. So because there are more than 2 groups, we don't know between which groups the difference are. The Crooks or Wallis test doesn't have post hoc tests, as you can see. It doesn't have post hoc tests. Thus, we have to do Mann-Whitney tests in order to determine between which groups are different. I think you remember we did Mann-Whitney after doing t-test, right? So which means with this one, we have to do some Mann-Whitney tests so that we check where the difference lies. So this is painful, very painful. So if someone comes with a project which wants this kind of analysis, we won't be friends. I'm sorry. But what is happening here is, remember, we have got 1, 2, 3, 4, 5, 6, 7 groups. right? That's what we have. And we want to check between group 1 and group 2, between group 1 and group 3, between group 1 and group 4, between group 1 and group 5, between group 1 and group 6, between group 1 and group 7. Now we are done there. Then we have to do group 2, group 2 and group 3, group 2 and group 4, group 2 and group 5, group 2 and group 6, group 2 and group 7, and so on. Then we do again group 3, group 4, group 5. So this is kind of manual which we have to do because Crooks or Wallis doesn't bring what? Post hoc tests. So what you then do is you go back to your analysis. On the same output file, here you don't save and close because it's the same thing. So you are now going to be using Mann-Whitney as your post hoc, right? So you go analyze, then you go same thing, non-parametric tests, Ligas dialogues, 2 independent samples. Then you go to the defined groups, right? You go to the defined groups. You click here. This is where you are going to specify which of the groups are you going to compare against. So I want to compare group 1 and group 2 right now. Which was the what? Which is the office trainee and the clerical, isn't it? That's what I'm going to compare now. So then you say continue. Then you say okay. Then you get this output, right? Sorry. I forgot to change my grouping variable. Getting tired, right? Job cut must be the one here. 1 and 2. Okay, so here we go. Right? Then you check your p-value here, 0.457. Right? But you have to compare this with your alpha. And because you are going to use Mann-Whitney as your post hoc test, you have to adjust your alpha value. Right? You have to adjust your alpha value. So that is what we call Bonferroni adjustment or correction. So this correction needs to be done because we are going to be using Mann-Whitney test as your post hoc test to control for what we call type 1 errors. By this, we mean that the significance level needs to be adjusted to a stricter level by dividing your 0.05 by the number of tests you intend to do. So if you are going to continue, doing this, checking how many tests you are supposed to do here, there are supposed to be 21 of this. If you are going to continue doing this, you're supposed to get 21 tests, right? Then you divide 0.05 divided by 21. Then you get a new p-value, which is going to be 0.00238. So this value, which you are getting in Mann-Whitney, which is 0.457, you compare it against that new p-value of 0.0238. And you see that this is more than that value. So you reject, which means that there's no statistical significant difference between the clerical and the office trainee in terms of their salary. So you do it again for 1 and 3, 1 and 4, 1 and 5, until 21 tests. So this is painful. So that's your Crooks or Wallis. Understand? That's your Crooks or Wallis. Are we there? Any questions? Okay. So let's save our output. So we go file. Then we say save as. Then we say, I'll just take this one. Then I'll edit there. This is going to be Cusco. Wallis test. And Man Whitney you test. Well, they are going to be between one of them, right? Under one file. That's how you're gonna save. Understand? Then you save. Then you close. Are there any questions on Crooks or Wallis? No. Okay. Last but not least, we do have paid somebody tests. Paid somebody test is used when there are matched pair of participants and wish to compare for some differences on a continuous variable measured on two different occasions or under different conditions. Okay, I want to explain a little bit on paid somebody tests. Because many people, they would want to use paid somebody tests, but they don't handle the process correctly. And in many instances, when they come to my office, you would find that we won't be able to assist, because they didn't process the experiment correctly. Okay. Paired sample tests, we are checking a continuous variable before and after. We are checking a continuous variable before and after. So obvious, something should have happened in between. An intervention should have happened in between, so that you then check the after. For example, you may have a topic which you are teaching, right? Then before teaching this topic, you just give your students a test before teaching them, right? Then you record the marks. Then you then teach that topic, maybe for 1 week or 2 weeks, right? Then after teaching the topic, you give them the same test, right? You give them what? The same test. Then you'd want to check whether there's an improvement in performance before teaching the topic and after teaching the topic. However, you also have to be very, 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 very alert in terms of lining up your participants. You don't just line up your participants randomly. Participant number one in the before should be participant number one in the what? In the after. So which means you must have a control measure of measuring your participants or your subjects before and after. So many people, that's where they miss it. You see before someone has got 100 participants, but in the after someone has got 80 participants. It can't work. It can't work. Totally, it can't work. So you must have some measures. If it means you have to take their names, I know ethical is not allowed, but if it means that has to be done to make sure that you have control of your subjects before and after that, then that's what you have to do. But the moment when you miss the arrangement of the subjects before and after, then it can't work again. So that's when many people, they come to my office. I was doing a pre and post experiment, and okay, give me the variables and so that I see. Then you see here, you got 100, here 80, bye-bye. So it's very, very, very important when you want to use a paid sample test. Even it applies even to veterinary. You buy your 30 head of cattle, right? You measure their weights. Then you put them on a feeding scheme before selling them on the market. You need to know cow number 1. Which one is cow number 1? Which one is cow number 2? You need to have a way of knowing your cows before and after. Cow number 1 before, weight. Cow number 1 after, weight. The moment it differs, then that experiment doesn't work. That's the key thing about paid sample test, which you have to know. Before we analyze, that's the importance of this. Okay, fine, but that is missing data. That is missing data. We can take it out. That is missing data. Yes. But we don't have to mix our subjects. That's my point. And many people, they mix. It won't work because you are comparing whether there's an improvement after an intervention. That's the reason why you are doing a paid sample test. So that's the reason why I'm saying for every test which we do, you have an objective which you want to achieve from your research objectives, isn't it? So that's your objective. You want to check whether there's an improvement after an intervention. That's the objective. So the moment when you don't make sure that your subjects are the same before and after, then paid sample test doesn't work.
In case it doesn't work, you don't have, is there no alternative test you can use to run it in place of that?
There isn't.
Okay.
It means that objective, you can't achieve it anymore. That's the reason why it's very important to see statisticians during the research design stage of your data. You come to us as StatCon. We tell you these tips before collecting data, not coming to us after collecting data. Right? Yes. So you see, even here you can see, we've got this ID, right? So now we want to check Saubeg, which was the beginning salary of that employee when he or she joined the company, versus the current salary of that employee over a certain number of years. And the same employee, you see, that's the reason why we have got some IDs here. ID number 1, he started at this company earning 8,400. After so many years, he's now earning almost times 2, 16,008. We are not comparing ID number 1 with ID number 2. No, the same person before and after. So this is when the person joined the company, and after several years, the person is now earning this. Right? So we are making sure here that we are comparing the same individual by giving them the ID numbers. Right? So I've got many researchers who come to my office, especially from the Faculty of Education. Right? They've done this kind of things, but they don't ensure that participant number 1 before is same participant after. They don't ensure that. So we can't help. Okay. Now that you know the trick behind paid sample test, let's get into it. Okay, so let's go to our analysis. Analyze, compare means and proportions. So it is one of the t-tests, which is paid sample t-test. Then we click. So you can see, right here, we are comparing Saubeg. That's our variable number 1. versus sound now. That's our variable number 2, just like that. Right? Then you click options. Then you click options. You make sure that the 95% confidence interval is clicked. And also here, estimate effect size is clicked. Then we are good to go. Right? Then you click OK. Then this is the output. This is the output. Let's go to the notes. So we first test for the correlation. So normally when they are doing a paired sample t-test, right? If we are comparing these variables, the height, weight, obvious, there should be a relationship between these variables which you are comparing before and after. Most times there must be a relationship. That's the reason why you see that among our output files, we do have the correlation, paired samples correlations, right? Paired sample correlations, what is meant to do is to measure or to assess the relationship between these two variables which you are comparing before and after. So in order to do that, you must also have a what? A now and an alternative hypothesis. There's no correlation, there's correlation, right? And because we are not saying the beginning salary should be is lesser than the current salary, we are just saying there's correlation, right? So, which means we look at the two-sided. We are not looking at one side. So, which means we are looking at the two-sided. So we take our p-value from the two-sided, right? And that p-value is less than 0.05. So we reject the now hypothesis that there's no correlation, and we are saying there's a positive, strong correlation. So this value is positive. 0.8880 is positive. That's the reason why we are saying positive here. Then the issue of strong emanates from Cohen again. Although I didn't include the Cohen's guidelines here, but according to Cohen 1988, 0 to 0.9 means a weak or a small correlation. 0.3 to 0.49 means moderate or medium correlation. Then 0.5 to 1 means strong or large correlation. According to Cohen 1988, I will refer you to Julie Palland. Those guidelines are there, right? Although I didn't include them in my write-up or in my notes. So I'll refer you to Julie Palland IBM SPSS Survival Manual under correlation analysis. You get those specific guidelines which I've just shared with you. Understand? Because you can't just say strong without referring to anything. Very important, we are researchers. You always have reference. You have to quote every time. Okay, so beginning salary and current salary, we saw that there's a very strong positive correlation. Now let's move on. Now we have to test for the pay differences, whether there is a statistically significant difference between that beginning salary and the current salary. And we also need these two hypotheses. There's no difference and there's a difference. Then we go to our we go to our results. This is the table which I took to our notes. Here it is. I also look at the two-sided, and the p-value is less than 0.05. So we reject the now hypothesis, which is saying there's no difference between the beginning salary and the current salary. And we are happy to say there's a difference, right? Yes. Then we go to the paired sample statistics. We get them again from the from our results here, then we see that on average, the 474 employees, their beginning salary on average was 6,800, but on average now their salary is now 13,000 something. So I think that's why the difference is statistically significant, right? Then at last, the effect size, and according to SPSS here, we do not have the data squared here. We have the coins D and the H correction. Whoever has got some literature to compare with this, please help me. Myself, for the time being, I know the data squared, which I'm employing here by using the formula. So you take your T squared from this table here. So this is your T value minus 35.036. Obvious, when you square it, it becomes positive. You square it again on the denominator, plus 474 minus 1 degree of freedom. You simplify everything, you get 0.72 to 2 decimal places, which is very more than 0.14, the large effect of CORE 1988 guidelines. Yeah. So, which then means that the difference between the beginning salary and the current salary was very, very huge. Right? Done. Paid somebody test, done. Any questions? I think also this is where I'm ending. I know just after paid somebody test, there's Wilcoxon sign rank test, which is the non-parametric version of it. You go through the notes, very easy. Yeah, I'm done. Any questions on what I've covered so far, or anything around what I covered before or here, or anything else? Yeah. Any questions before we call it a day? Online in the end.
And to the online audience, we have enabled everyone's mic. So now you can just unmute yourself if you want to ask any questions.
Mr. Again, let's not forget to scan these codes, the attendance and the feedback survey. Please and thank you.
Yes. I'm not getting you.
Another name for these is dependent details, right?
Another name for?
Pair sample details.
I don't know of any. Yeah. What I know is the non-parametric of it is Wilcoxon sign rank. Yeah. But it's the non-parametric version of it. Any question?
And nothing in the chat.
So we are happy, right? Okay, happy days then. Maybe we can close if we don't have anything. Yeah. And just remind them that next workshop, only physical.
Okay. Participants that are online, I'd like to remind you that the remaining SPSS training sessions will be done in person. We will not be having a hybrid session.
SZS, you can unmute your mic.
Yes, thanks, all stakeholders present, and Prof. I would request that maybe we have some of them hybrid, because for me to get there, it's impossible, clubbed with the working conditions and the days and times when these sessions are held. But they are very, very informative. So I would still request that maybe we go on to the hybrid. We also explore the hybrid method as well. It's a special request. Yes, thanks, Prof, and the team and all stakeholders.
I think in that regard, you can just share the coding to those who didn't make it. Because we are receiving a high number of participants who are registering to come here physically, but then on the day it turns out only the facilitator and us organizers have put so much effort to try to organize such workshops. So going forward, we prefer to make it physically such trainings, and those who have conditions to make it to the venue, they have to. And those that don't have that such conditions, they have to access the recording. We keep on recording our sessions.
Thank you.
Right. Thank you. I would like to appreciate the participants for joining us in today's training. I am going to now be stopping the recording and concluding the workshop. Do enjoy the rest of your day further, and goodbye.
Thanks and cheers.